So welcome to the today's class. Today I'm going to discuss about introduction to integrated circuits. Okay. In the last class we have seen the basic VLSI design flow. Okay. And in that VLSI design flow, we have seen that we have started with the specification or an idea of what we want to design. We started from there, and we concluded that okay, we have to create a GDS2 file. Okay, once we create the GDS2 file, that will be given to the fabrication engineers. Okay, they can fabricate the IC, whatever we have specified. Okay, but as we mentioned that it is not a straightforward approach. It consisting of a different steps involved in it. Okay, broadly we have classified the VLSI design flow into two parts. One is called fundamental VLSI design flow. The second one is called fabrication. Okay. Again, the fundamental VLSI design flow consisting of two important steps. One is called pre-RTL flow, and the next one is called GDS flow or PD, physical design. Later, we have seen the post-GDS, that is called the fabrication, right? Now, let us understand about brief introduction to the integrated circuits. Okay. So this is the lecture plan. Okay, I'm going to introduce ICs and the figure of merit in this class. Now, what is an integrated circuit? Let us define this one. An integrated circuit is an electronic device made from semiconductor material. Okay. Usually a silicon. Most preferably, people will use the silicon, but basic element. On the silicon material, we are going to create thousands to billions of teeny electrical components such as transistors, resistors, capacitors combined together. Okay, so therefore we are going to create or we are going to modify the semiconducting material to make this kind of components. Okay, especially transistors, resistors, and capacitors. Okay. These components are interconnected to perform a specific task such as amplification, computation, or data storage within a single chip. Okay, what purpose that we are creating these kind of teeny elements or teeny components in a silicon wafer in order to perform some kind of tasks. What are the tasks that we want to perform? So some kind of amplification, storage, data storage, or maybe computation purpose. If you see that, this is how the chip is look like. Okay, this is an open top. The chip is having on top of it, there is the coverage is there, but inside of it, there is a die. Okay, what we can call this is called die. So once it is packaged with this die, this is called a chip. This is called a chip, right? Let us look at this die actually. Okay, so therefore, whatever you can see here, okay, whatever you can see here, this is actually a die. It is actually shown in an enlarged fashion in this way. It consisting of millions to billions transistors or components. Components in the sense, it can be a transistor. Most preferably, it's a transistor. Resistors and capacitors are minute things in this particular design, but essentially all are transistors. Majority of things are transistors. From the transistors to the gates and gates to the some large components can be created on it, right? Fine. Now let us classify ICs. Okay, what are the different type of ICs that we can see? Actually, ICs are classified based on the number of components in that particular IC. That is the scale, how many number that will be represented by the scale, and which domain that we are using. whether analog device, analog purpose that we are using, or digital purpose that we are using, or mixed purpose that we are using, or generally what kind of application that you're using for this particular IC, which purpose. For example, application specific oriented that you're using, you are creating an IC, or general purpose that you're using an IC, right? Okay. So if you want to define the IC based on the scale, we have different kind of things here. One is called small scale integration, medium scale integration, large scale integration, very large scale integration, and ultra large scale integration. So that means, how do we define the IC here in this case? Based on the scale. That means number of components. Scale in the sense number of components. Okay. So for example, if you say that the SSI, small scale integration, means that approximately, okay, 10 transistors to 100, sorry, 10 transistors to 100 transistors, or otherwise we can simply call it as 10 components to 100 components. Okay. So what kind of purpose that we use this kind of transistors, this kind of integration or ICs? Basically, we use for this one is simple gates. So if you want to realize the gates, we go for this kind of approach, or simple flip-flops. Okay. Because the simple gates and the flip-flops doesn't require more than 100 transistors, right? Below the 100 transistors only. Okay, when we go for the laboratory, for example, any digital logic design laboratory, you'll see the ICs, small ICs that you can see, right? Those ICs are integrated based on the small scale methodology. Okay, it doesn't require many more steps involved in it. The next one is called medium scale integration. Okay, so what we can see here, the medium scale is consisting of, for example, more than 100 transistor to, okay, and 1,000 transistors or components. Usually, actually, it's not accurate value, but around that kind of thing, right? Okay. So what purpose that we design this kind of things? Generally, for example, multiplexers, okay, counters, registers, okay, and the small memories. So if this kind of purpose we are using the medium scale integration, okay, because definitely it requires the less than 1,000 transistors. Okay. Next one is called large scale integrated circuits, which means that 1,000 to 10,000 transistors or components. That means whatever the chip that you are creating, that chip consisting of 1,000 to 10,000 transistor can have, or components can have. So, okay, what kind of designs that you can create under this scale? So we can create mostly the small processors that we can create, as small RAM chips that we can create. Okay, not only this one, but many things that I am mentioning small things here. Okay. Yes, definitely it requires around 10,000 transistors or components are required for this. Now, if you go for the very large scale integration, it is 10,000 to, okay, millions of transistors. Okay. Okay, what kind of things that you can create, or what kind of applications we use the VLSI integration? Mostly we go for the microprocessors, advanced chips, advanced memory chips, and large CPUs. Okay. Okay, these are the applications where we normally go for very large scale integration approach. Okay, because it takes 1,000 transistors to millions of the transistors. Okay. Next we go for ultra large scale integration. That means it is from millions to billions. Okay, now it is the people run behind the ultra large scale integration. Okay, as we know that high-end processors, system on chip, SoCs, okay, high-end processors that we can create for this one. Okay, because that needs these many number of components. Are you getting the point? Okay, so that means IC is classified based on the scale. That means the number of components that we can provide on that particular IC, right? The next one is whether you're using, what purpose you're using your IC, for analog purpose or digital purpose or mixed signal purpose. What does it mean? For example, amplification purpose, if you want to use your IC, okay, then definitely we go for analog ICs. That means it will process the continuous signals. Okay, IC will take the inputs in the form of continuous signals and then produce output as also a continuous signal. Whereas if you take the digital signals, the input must be a digital in nature, okay, and the output is also, will get the digital output that we can get it. Sometimes the application can be both analog and digital also required. In that case, some part of the IC will be dedicated for the analog representation, some part of the IC will be dedicated for digital application. Both combinedly work together. Okay. Next. Okay. Whatever IC that you create doesn't matter, analog purpose or digital purpose. Okay. Whether small scale integration, large scale integration, doesn't matter. Okay. What purpose that you are creating, what purpose you are designing this IC, whether you are creating this IC for exclusively for a specific application or for general purpose. For example, you consider it in this way. For example, in your camera, for example, a certain kind of application is required. Okay. For example, high definition module is required for that one. Okay. That particular design is created in the form of a chip, for example. That chip is exclusively for the camera purpose. Okay, we cannot use that one for any other cameras. Okay, for example, mobile applications, we are using the camera that is exclusively for that particular camera, mobile camera only, not for any other general cameras. It won't work on that one. Okay, exclusively for that one. Okay, so that kind of ICs we can call it as application specific integrated circuits. Okay, whereas general purpose IC is not like that. Okay, you create a IC that can be used for multiple purposes. You can use anywhere. What purpose that you can use it also. But how they can create this general purpose ICs, we will see. As for example, we see a microprocessor, for example. Microprocessor is actually a general purpose device. We can perform n number of applications on it. Okay. For example, if you create one IC, for example, you create an IC only for addition. For example, hop adder, for example, sum and carry. Okay. Later, this IC would like to change this one to, for example, 3-input adder. Okay, that means full adder you want to create. Definitely, you have to create another IC, undoubtedly. Okay, but whereas the general purpose IC is not like that. Okay, so you can modify this particular IC by configuring the another input. Okay, or if you want to perform the multiplication of these things, for example, A, B, and B and C, it will produce only one output. Multiple applications can be done by the same IC. You did not create another IC for that. That kind of ICs we can call it as general purpose ICs. Okay, usually FPGA, for example. Okay, we can implement any logical functionalities based on in an FPGA. All right, good. So these are the broad classifications. Let us go and see another thing. But how do we implement these ICs? What are the different ways that you can implement these ICs? or design styles by which we can create this IC. Okay, we have four essential, the four ways that we can do this one. There are the four ways that we can do here. So what is the first one? We can call it as full custom design. Okay, the second one is called standard cell based design. Third one is called gate array based design or semi custom design. The fourth one is called FPGA based design. So these are the ways or design styles by which we can implement our ICs. Let us take what is the advantage, what are the different aspects that we have to see for each and every design style or implementation style. Okay, now look at this one. First one is customization. What do you mean by customization? Customization means that according to your requirement at that particular point of time, are you able to change the, are you able to configure your IC or not? Okay, so for example, today I'm using FPGA, for example. Okay, today I'm going to realize, for example, division on that particular FPGA. After 1 hour, I want to realize multiplication, for example. Am I able to reconfigure that FPGA for that purpose? Yeah, that is called customization. According to your requirement, you can change the configuration. Okay. So therefore, we normally you go for the customization. So if you create an IC based on the full custom design, okay, you have to use it's a completely customization, right? Okay, so during the fabrication we can say that whatever the way that we can realize, whatever the things that we can realize it before fabrication. Okay, you can do that one, because everything we can start from the scratch. Okay, maybe a transistors, resistors, capacitors, logical function, logical blocks, whatever it is, you can do it from the scratch. But in the standard cell based design, pre-designed cells will be there in it. Okay, maybe add a cell, NAND gate, NOR gates, or medium scale integrated circuits. All the things will be available here. So just only the customization is on the interconnects. Okay, the standard cells are available. Okay, for example, AND standard cell, add a standard cell, multiplexer standard cell, all these things are available, right? You did not do any kind of you did not do anything with that one. Just only thing is that we have to provide the interconnects between the standard cells. You have to provide the interconnects between the standard cells. Okay, next one is called gate array based design or semi custom design, where what we can see is that the predefined gates are available. So what is this layout of this one? What is the height, width? Okay, what is the power, area? Okay, and what is the dimensions of the gate? All the things are predefined. You need not do anything with that one. Okay, but thing is that it is possible to provide the customizable interconnects can be possible. Okay, the next one is called FPGA based design. It's a predefined all the blocks, but it is possible to customize the interconnects. But instead of customizing the interconnects in the FPGA point of view, we can call it as reprogrammable. We can call it as programmable. So this provide the interconnection between the components. Okay. So therefore, there is a lot of thing that we can understand the full custom design. But see, look at this one. Everything from the scratch here. Everything from the scratch. But here, something we can take it. Something is actually predefined, and the only we focus on the interconnections between them. So all these three cases. Okay, either the cells that you are cells you are taking, or gates that you are taking, or designs, whatever the logical blocks that you can design, CLBs that you are taking, that's a different story. But only in all these three cases, you have only the interconnection between them. The next one is performance. So since you are realizing everything from the scratch, okay, there's a high performance and efficiency can be expected in this one. Okay, because if you're designing something, you're not getting proper performance and efficiency, definitely you can change that one and you can modify that one at that point of time. Therefore, you can expect efficiency and accuracy, and high performance can be possible with the help of full custom design. Okay, if somebody asks you what is the advantage of using the full custom design, you should say that it's a very high performance and very good efficiency can be possible. Okay, but whereas standard cell based design is performance is a little bit less than that of the full custom design. What is the reason? Because the standard cells we are taking from somebody, right? They have defined already, their performance is defined already. If you want to improve that performance, it's not possible, right? Because the standard cells, you don't have any control on the changing the layer, changing the standard cell of configuration. We have only the interconnections, but once one gate to one standard cells to another standard, so how fast that you can go, that only that you can control. Okay, therefore high performance is possible, but less than that of the full custom design. So, but here in the gate array designs, gate array based designs, moderate performance can be achieved, but very low performance is achieved because of the reprogrammability. Because the FPGAs are completely predefined the things. Okay, what there in the FPGAs? Combinational logic blocks. What is there in this one? Combinational logic blocks. Their performance is actually predefined. Okay, you need to compromise the performance because majority of the things and interconnects also. Okay, see what is happening here. For example, if you are connecting the two blocks in an FPGA here, they will provide the blocks where the blocks are available, and they will provide the interconnection between them also. Just we have to reconfigure. That means, for example, if you put the some kind of Verilog code and then dump it into this particular one, and it will choose one particular path. Okay, there is no optimization at this stage, right? You give the notation, and accordingly it will be provide the information on that one. So accordingly it will be connected from one device to another device. Okay, therefore here you can expect that if some particular path is not suitable, then you cannot go and create another path for that one. Okay, so therefore it is having the lowest performance when compared to other three categories. Okay, so in spite of the performance is very high, it takes a long time to design the IC. Okay, so several months it will take to create an IC. Whereas a shorter time that will be taken for the standard cells, and shorter here. But here is the shortest design time. Why? Because when you have money, then you can go and buy that FPGA. That's it. You need not wait to do some kind of the fabrication or so and so thing, right? So your application and what kind of FPGA is suitable for this one. Go to the market, buy that one. That's a very design time is very less, right? Yeah. So since that is the reason why if the cost of this one is very high with the full custom ICs, okay, but whereas other things are very less in cost. But one thing is that the cost of the full custom design also can be reduces if the number of components are high. Okay, then the volume, if the volume is high, then definitely it will take a little bit on the cost side as well. Let us talk about the flexibility. Okay, no flexibility after the fabrication. Okay, once it is fabricated, no choice. You have to rely on that. And limited flexibility in the design. Okay, because the standard cells that are, whatever the predefined standard cells that are there, we have to use that one. Okay, limited scope is there. Here also limited flexibility, but here high flexibility. Okay, here we can say that high flexibility. So what are the different way that you can write the program? Accordingly that you can change your logical structure. There's a lot of flexibilities there in the FPGA design based ICs. So look at the power consumption here. So therefore everything is optimized in the full custom design. That's the reason why it is the lowest power consumption is achieved. But whereas high power consumption is achieved in the FPGAs and then gate array structures and moderate design. So where these full customizers that we can use, most preferably high performance CPUs, GPUs, and custom chips, they will use the full custom approach. Okay, because they required that one, they needed that one. Next one is called general purpose digital ICs. General purpose, if you want to create, go for the standard cells. Okay, for example, medium performance ASICs that you want to go for, and go for the gate array based designs. Okay, and you can see that this is what important. So for example, if a research purpose, if you want to prototype something, okay, if you want to prototype something, then definitely you have to use application. So definitely you have to use FPGAs. Okay, for the research purpose, or you have an idea, you want to model that idea very quickly and you want to see its performance, then definitely go for the FPGAs. Okay, the scalability, not scalable after the design, scalable with moderate changes, some scalability, but highly scalable and adaptable. Okay, so therefore these are the things that we have to remember about the implementation styles of ICs. Okay, so accordingly, according to your understanding or according to your advantages, that you have to go for any one of the approach. Am I clear to everyone? Okay, put some kind of attention in this one and get some kind of idea for this. Okay, hopefully I've given some kind of basics in this particular one. Okay, let us conclude this one with the help of something like this. So whenever you talk about the full custom design, okay, so best performance and efficiency can be possible, but with the high cost and longer development time. Okay. Next, for the standard cell designs, what we can do is balance in the customization with the design time and cost and marketing. It deals for many digital ICs and ASICs. People will go for the ASICs or maybe digital ICs. People will go for the standard cell approach only. Okay, because design time is a little bit less compared to the functional, and the time to market and the costing is also less compared to the full custom designs. Whereas the gate array structures, it is a semi-custom approach. Okay, so design time and cost is also very less here, but we need to sacrifice the performance and flexibility in it. Next, FPGA based design. Okay, it is the greatest, producing the greatest flexibility and the shortest design time. Okay, so it is mainly advisable for prototyping, researching, and low volume production. Okay, and though with low performance and high power consumption, people will go for the prototyping, researching, and different low production ICs that we can go for this particular one. Okay, this is how we can conclude about this. Next one is we focus on the mainly digital ICs in our course, right? So especially we are going to use application specific integrated circuits and general purpose ICs. Okay, we observe here is that same thing here. So application specific means that what? Okay, that IC is exclusively for one particular application. It cannot be used for any other purpose. Okay, but whereas general purpose we can use anywhere. Okay, you can reconfigure whatever you want to go for it. Okay, so for example, GPUs, network chips, generally we go for the ASICs. Okay, use it for many applications, microcontrollers, op-amps and FPGAs. For this purpose, we use the general purpose ICs. Flexibility is that fixed functionality. Please look at this one. We are not going to change this functionality at all. Once a specific application is that is fixed. As I mentioned that if it's a full half adder, for example, if you want to convert it to full adder, it's not possible. So, but here a lot of flexibility and the configurability is possible. Performance optimized for specific performance. Okay. You can optimize, because this is also just like the full custom design approach only, because actually we can optimize the performance as much as possible by providing the interconnections in a different way and placing the components in a different way. But whereas it is less optimized but versatile. So development cost is very high, okay, but later if it is a mass production, ASICs are very less in cost. But whereas here, so lower upfront cost, okay, with less amount of the less amount that we can get the things. Longer duration time, it's a shorter. Power consumption is lower, it's a higher, okay, because actually it is we can optimize this one. No, there's a reason why we can optimize the power. So high for low volume and low for high volume that we can see, but always we can see that whatever it is there, it will be low in cost only. The scalability is that not easily scalable, fixed after the design, but easily scalable and reusable. Okay, because the resources that are available, you can reconfigure that one and make use according to your requirement. Okay, so what is your conclusion in this particular thing? So ASICs are ideal for high performance, high volume applications where you need a customization, power efficiency, and optimization for a specific tasks are essential. In that situation, we have to opt for ASICs. Whereas general purpose ICs, for example, so more flexibility is available within less time that you can design your ICs, and adaptability across the multiple projects or industries, right? Okay, it's not specific to only one industry or one particular task. It can be a many purpose. Now let us see the figure of merit. How do we identify that your IC is good? The IC can be good based on these parameters. One is called power consumption, performance, area, testability, reliability, and scheduling. We focus on low power consumed ICs. We want high performance ICs. We want low area ICs. The same way, it must be testable. Okay, once the fabrication is done, if you want to test your IC, you did not focus you did not afford a lot of, you did not afford a lot of things on that one. Okay, with less effort that we have to test your IC. And reliability, okay, how the durability, how much reliable that your IC is. Okay, how can we give the assurance for this one? And whether it is a time to market or not, we have to schedule that one. Okay. But most importantly, we focus as a digital designers, people will more focus on this particular one. Okay, so this is called PPA. Okay, power, performance, and area. We must be focused on that one. The priority will be given to the power, performance, and the area. Okay, always we focus on low power chips that we have to create, high performance chips, and then low area chips that we have to design. So these are the things that we have to understand. How do we measure the power? It is the combination of the static power and the dynamic power. Okay, how much the static power and dynamic power is consumed by the IC that we have to measure, and based on that one, if the value is less, we can say that low power IC. So performance is that maximum frequency of the clock at which IC will work. Okay, what is the frequency, clock frequency it is allowed to perform the particular task. If the frequency is high, then definitely it will be a fast IC. And area of the dice for an IC also we have to consider. Okay, so these are the things we need to understand. So these are the references that we can design. I followed. Please go through it once in your lectures. Okay, thank you. We stop here today, and the next class we will see the importance of HDL programming. Right.